Hello guys, good day to you, and you are welcome to our class for today. This is Normal Science Tutors Online, and for today we are going to be looking at electromagnetic field. Electromagnetic field. Remember that we have we've had some lectures on magnetic field, and we have also discussed some instrument or devices that work based on magnetic fields. So for today, we'll be looking at electromagnetic fields. We'll also look at the direction of the current in an electromagnetic field, and we'll look at the force between conductors carrying current in a magnetic field, and then we'll also treat Fleming's left-hand rule. Fleming's left-hand rule. Then we'll solve some problems that has to do with the force on a charge in a magnetic field. So you are welcome to our class. Please, if you have just visited our channel, subscribe to the channel, click on the notification bell so that when we upload a new video, YouTube will notify you. Also give us a like, give us a thumbs up, and give us a positive comment, right? Please, if you have been visiting this channel, thank you so much for visiting. If you have any challenge, please reach us through the WhatsApp link that is showing down on this video. Okay, so please get your writing materials ready so that we can go straight to our class for today. All right, so if you are ready, let us go. So as I said, today we are going to be looking at electromagnetic field. Remember, when we treated magnets or magnetic field, we said that a magnetic field is a region in which the force of a magnet is felt. Okay. Then we also said that electromagnet is a soft iron core in a current carrying solenoid. All right. So today we are looking at electromagnetic field, and electromagnetic field is a field that represents the joint interaction of electric field and magnetic field. So the statement electromagnet means that it is coined for electricity and magnetism. Alright, so it has to do with electricity and magnetism. So electromagnetic field is a field that represents a joint interaction between electric field and magnetic field. Okay, so electromagnetic field actually exerts a force on a charged particle. So if a charged particle is in the magnetic field of a bar magnet, the electromagnetic field will exert a force on it, and the force on a charge moving with a velocity v in an electromagnetic field is given by this equation. Force is equals to the quantity of the charge, the electric field plus the velocity and the flux density. B is electromagnetic flux density or magnetic density. Okay, so this is the equation for the force on a charge moving with a velocity in a magnetic field. Now we will now look at the force on a current carrying conductor in a magnetic field. Okay, so this picture here actually depicts what happens when a current carrying conductor is placed in a magnetic field. All right, so I don't have the picture for a U-shaped magnet, but this picture can actually suffice because these are two magnets. Okay, these are two magnets. These are two rays, and then this is a current carrying conductor. All right, this is a current carrying conductor. It's a copper current carrying conductor. All right, so when a conductor carrying an electric current is placed in a magnetic field, it experiences a mechanical force. And this can be demonstrated by a simple setup. So this setup can be used to actually demonstrate that when a conductor such as this copper rod is placed in a magnetic field, when you place two magnets like this side by side, there will be a magnetic field between the two. This is a north pole and this is a south pole. So there's a magnetic field between these two magnets that are placed side by side. So if you put a current carrying conductor in between the magnetic field, in between the two magnets on a reel, and then you complete your circuit here, a mechanical force will be experienced. Now, this is a simple setup. The setup is that two metal rays are fixed on each side of a powerful horseshoe magnet. Okay, so this could be a horseshoe magnet, but we can also use the two magnets to represent it, right? What we want to know is that the two magnets, they are placed side by side, right, with opposite poles facing each other. Then there is a copper rod that is placed across the rays. Okay, so these are the two rays, and then there's a copper rod. The copper rod is the current carrying conductor. So when current is passed through the copper rod by closing the keys, by closing this key, maybe you press this button to close the key. In this setup, it is observed that the copper rod rolls along the rays to the right. If the current is increased, the copper rod will roll faster. Also, if the direction of the connection is reversed, the rod will move to the left direction. To be observed that the rod will move to the left direction. So this observation tells you that there is a current that is flowing on this copper, and that there's a force, a mechanical force that is experienced by this current carrying conductor in a magnetic field. That's okay. Now, if the magnet is turned so that the magnetic field is parallel to the length of the rod, if the magnets they are turned so that the magnetic field is parallel to the length of the rod, it will be observed that the current carrying rod remains stationary. So what that tells you, that which means that the angle between the magnetic field and the rod is 0 because they are parallel to each other. So the angle between them is 0. Don't forget that aside this equation, there's an equation that we have derived, that the force on a current carrying conductor in a magnetic field is also given by QVB times sine theta. Theta is the angle between the force and the direction of the current. So if theta is equals to 0, it means that the force will be equals to 0. So which means that there will not be any force acting on that current carrying conductor, hence it will not move. So take note of that. F will be equals to 0. So that means that when the magnet is placed parallel, so that it is placed in such a way that the magnetic field is parallel to the length of the rod, the force on it will be equal to 0. Hence, the rod will not move. No matter the force you put in, it will not move because the force will be equal to 0. No matter the current, right, it will remain in one place, right? So this, you should take note of this. Then the direction of the force acting on the conductor depends on the direction of the magnetic field and the current flowing. So these 2 points, you have to take note of them. All right, these are questions that you can be asked in your theory in physics. So the direction of the force acting on the conductor depends on the direction of the magnetic field and then the current flowing. Don't worry, in a short while we are going to look at the direction of the force on a current carrying conductor in a magnetic field. So for now, you have understood what it means to say that a current carrying conductor in a magnetic field experiences a mechanical force. Okay, So once you have understood that, then we can now go to the direction of the force in a current carrying conductor. Okay, so this is what I've discussed already, that for a current carrying conductor placed in a magnetic field, it is observed that whenever a conductor carrying current is placed in a magnetic field, mechanical force acts on the current carrying conductor. That is what we just discussed. Then the direction of the force is always perpendicular to the direction of the magnetic field and current. Okay, that we're also going to discuss. What that means is that the direction of the force, this one, the direction of the force is always perpendicular to the direction of the magnetic field and then to the current. Okay, so that is what they are telling us. Okay, so assuming this is the force, direction of the force, then this is magnetic field, and then this is your current. Okay, we shall come to this discussion later. Then the magnitude of the force produced proportional to the current and the field strength. It decreases with increase in the current and field strength. The magnitude of the force decreases with decrease the angle between the conductor and the force field. Okay, and I also want you to know that the magnitude of the force is at maximum when the angle between the conductor and the force field is equal to 90 degrees. So take note of that too, that it is maximum when the angle between the conductor and the force field is equal to 90 degrees. So F is equal to maximum when theta angle is equals to 90 degrees. Please, you have to take note of this. These are simple examination questions, objective questions that you might come across. All right. So let's go to Fleming's left-hand rule that tells you the direction of the force on a current carrying conductor in a magnetic field. So the direction of the force on a current carrying conductor placed perpendicular to a magnetic field is given by Fleming's left-hand rule. The rule states that if the thumb, the forefinger, and the middle finger are held mutually at right angle to each other, with the forefinger pointing in direction of the field and the middle finger pointing in the direction of the current, then the thumb will point in the direction of the force or the direction of the motion. Okay, so this is what is represented by also this picture here. This is your thumb, this is your forefinger, and this is your middle finger. So when they are held mutually, this is what they represent. The thumb represents the direction of the force with direction of motion. The first finger represents direction of field, and they represent direction of current. And this is what we have here. Theta is the angle between the field and the current. Okay, angle between the field and the direction of the current. So this is Fleming's left hand rule. This rule is very, very key and important. So you have to take note of it. And mathematically, it has been stated that when a current carrying conductor of length L is placed in a magnetic field and the angle between the field and the current is equal to theta, then the force between them is equals to magnetic flux times the current times the length times the sine theta. Okay, so this equation you still have to take note of it. Okay, take note of this. Then I said that when theta is equals to 90 degree, the force is maximum. Okay, the force is maximum. So you remember that sine theta 90 degrees equals to 1. So please take note of this equation and also take note of this Fleming's left hand rule. Very, very key. All right, very, very key and very, 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 very important. All right, so now we'll look at other areas of this electromagnetic field, and that we are going to look at the force between conductors carrying current, two conductors carrying current. So assuming you have two parallel conductors placed side by side and there is current flowing in this conductor, what will be the effects of the magnetic field between them? Will it be attractive or will it be repulsive? Alright, so when two parallel current carrying conductors are arranged side by side, each conductor will lie in the magnetic field of the other. Alright, because each of them has their own magnetic field. So this conductor will be in the magnetic field of this, and this will be in the magnetic field of this. So which means that the two of them, they will exert a force on each other. Now the direction of the current flow in each wire will determine whether the force between them will be attractive or repulsive. So if the direction of current flow in the two conductor, they are in the same direction, like look at this one, the current is flowing in the same direction in these two current carrying conductors. If they are flowing in the same direction, then the force between these two conductors will be attractive. So there will be attraction between the two. That's what you are seeing here. Where you have more flux density, where you have the where you have the magnetic field closer to each other, you have a stronger flux density. Okay, where they are far apart, then the density there is weak. Okay, so when the current between the two is in the same direction, there is attraction. When the current is in the opposite, like this one, the current is in the opposite direction, so there is repulsion. All right, so when the current is in the opposite direction, I want you to take note of this diagram. These are diagrams that they give to you in your objective. They will just draw the drawing, they will just put the diagram, but what the key is for you to look at the direction of the arrows. So if you bring out any physics question and you see it is there, I've seen many questions like this from past physics objective. What the key for you to understand the direction of the current is for you to look at the arrow. Yes, an examiner can draw this arrow will face like this one will face the other, but they will draw it like this. So you have to be careful when you see questions like this, but please take notes and look at the directions of the arrow. That is what will guide you. Alright, so when the current are flowing in the same direction, the force will be attractive. When they are flowing in the opposite direction, the force will be repulsive. I hope that is clear and understood. Alright, so now we are going to look at the motion of a current. All that we are discussing so far is the effect of electromagnetic field. Alright, all that we're discussing is the effect of magnetic field. Then we're looking at the direction of the electromagnetic field, direction of motion and all that. Okay, so now we want to look at the motion of current, the motion of a current carrying coil in a magnetic field. That's what we want to look at now. Okay, so if this is a coil and it is placed between two magnets, as we have discussed before, there is a magnetic field between these two magnets. So there is a force that will act on this coil that is in between these magnets. So we want to look at the motion of this coil that is placed in this magnetic field. Alright, so when current flows around a coil placed in the magnetic field produced by a strong magnet, is that okay? If current flows through this coil that is placed in this magnetic field that is produced by a strong magnet, assuming these two magnets they are very strong, and this is a coil that is placed in between them, and current is flowing through this coil. An equal and opposite force are exerted on the sides of this particular coil. Equal and opposite force are exerted on the side, that is this side A, B, and CD. Equal and opposite force are exerted on the side. The direction of the rotation of the coil can be determined using the Fleming's left-hand rule. Okay, the direction of the rotation of coil can be determined using the Fleming's left-hand rule. Remember that the Fleming left-hand rule, the direction of motion is the thumb. The direction of motion is in thumb. Is that okay? So if this is, if you have your current and you have your force, this is your thumb, this is magnetic field, and then this is your current. Okay, so we can look at this picture and then know the direction of the rotation of this coil. The forces on the sides of the coil represent a couple. Yes, because why? They are equal and opposite forces. And what is the effect of a couple? The effect of a couple is rotation. So if the effect of the couple is rotation, it means that this coil will rotate in a clockwise direction. So simply put, it means that this side A will come up and then this side CD will move down. Is that okay? So that is how it will rotate. This side AB will go up, we experience an upward force, while the side CD will experience a downward force. So the equal and opposite forces that forms a couple will cause this coil to rotate in a clockwise direction. If the direction of the coil is reversed, or the direction of the current that is flowing into the coil is reversed, then the coil will rotate in the opposite direction. Now the force rotating the coil can be increased by 1 if you increase the current that is flowing into the coil, that is 1. If you use very powerful magnet, that is 2. If you increase the number of turns of wire in the coil, that is if you make more wires on this coil, and if you increase the area of the coil. These are factors that can make the rotating of this coil to increase. Okay, so these are factors that will make it to increase. So you take note of this. These are key information that you need for your examinations. So any information that I put a sign like this, know that is very, very important. All right, any information that I put a sign, know that these are typical questions that you can see in your JAM and wire connect physics objective. That's okay. So know the rotation using the Fleming's left-hand rule. Okay, so the rotation will be in the clockwise direction, but if you reverse direction of the current, the rotation will also change. Take note of that. All right, so please, these are very key informations that you need to take note of. So right now we'll go to some questions and see how we will apply the equations on the force on a current carrying conductor placed in a magnetic field. All right. So this is question number 1. This question number 1, and this question says that a straight conductor of length 0.60 meter moves in a magnetic field of flux density 1.57 Tesla. When a current of 10 amp flows through it, calculate the 1 force moving the conductor when it is inclined at an angle of 30 degrees to the magnetic field. The maximum force acting on the conductor in the magnetic field. So first is we'll write down the equation, the force. say that force is equals to B times I, which is the current, times the length of the conductor times sine theta. Okay, so here we are giving B to be equals to 1.57 Tesla. Alright, we are giving a current to be 10 amp. We are giving length of the conductor to be 0.6 meters, and we are giving the angle to be equals to what? 30 degrees. So having done this, we can now say that for the first one, number one, F is equals to this. So we're substituting to that equation to give us 1.57 multiplied by the length, which is 0.6, okay, multiplied by the current, which is 10, and multiplied by sine 30 degrees. Sine 30 degree is equals to 0.5. So if you work this out, you will have that the force F is equals to, punch your calculators, you will have that F is equals to 4.5 Newton. So that is your first one. Then for the second one, we are told that the maximum force acting on the conductor in magnetic field. Remember, I said that the force on the conductor is maximum when the angle between the magnetic field and the current is equals to what? 90 degrees. So for that second one, it means that theta is equals to what? 90 degrees. So put it that the force now is equals to 1.57 multiplied by 0.6 times 10 times 1, cos sine 90 degrees is equals to 1. I hope you know that sine 90 degrees is equals to 1. Alright, so by the time you multiply this out, you are going to have 9.0 Newton. Alright, so this one will give you 4.71 when you use your calculator, and then for the second one you have 9.4 Newton. It's 4.71 Newton and this is 9.4 Newton. Alright, so this is how to apply the equation to solve the force on a current carrying conductor in a magnetic field. Let's do another one. Okay, so this one said that a conductor of length 2 meters carries a current of 0.8 amp while kept in a magnetic field of magnetic flux density 0.5 Tesla. The maximum force acting on it is what? Remember, this is a jam question, so you are not expected to waste much time. So your own is to write the formula and know that maximum force is experienced when theta is equals to what? When theta is equals to 90 degrees. Okay, so it's a jam question, so no time to waste. We'll just put your variables. That is 0.8 amp, current is 0.8 amp, length is given to you to be equals to 2 meters, and your flux density B is given to you to be 0.5 Tesla. Okay, so just put them into your formula. Write your formula. F is equals to B multiplied by L times I times sine theta. Okay, so put your values. B is 0.5, length is 2, your current is 0.8, and your angle is 1. Okay, so by the time you put in your values, by the time you press them in your calculator, you will have that the force is equals to um, 0.8 Newton. Alright, so F is equals to 0.8 Newton. Alright guys, so I hope this is quite simple. It is for you to understand the equation that you are being given and then know which of this equation to you to solve. But no, when you have maximum force, you are talking about angle being 90 degrees. So just take note of that point so that when you have any question, you can solve it easily. Okay, so thanks a lot. Let's look at your review questions. Okay, so this is your test your understanding page. I think all these questions, they are just like what we have solved, but just try your hands on them and then see how far you have been able to understand this segment of our discussion or this topic. All right, so this year we are stopping this class. We thank you so much, and we stop here for today. So before I leave, please subscribe to our channel, give us a thumbs up, give us a like, give us a positive comment, and then click on the notification bell so that when we upload a new video, YouTube will notify you. You can reach us through the WhatsApp link that is showing down on your screen. If you have any challenge, paste it there. We'll look at it and see how we can assist you. We appreciate you for being with us. Please reach out to your friends, tell your friends about this channel. Our aim is to help students who are finding it difficult to understand this all important subjects. You know, physics is one of the subjects that makes the student not to want to study sciences. So we are trying our best to make sure that we make this subject as simple as possible, and we have tried to cover the full curriculum of WAEC, that is for West African students, and not only that, all other students all over the world, right? So thank you for your time, and we hope to see you in our next class.